We'll continue with the design of staircase, part 2. Okay. Design a dog leg base slab type staircase supported at its edges perpendicular to the riser. Okay, perpendicular to the riser means this is your support which is perpendicular to the riser. Okay, in this case, and the land and the going will transfer its weight to the landing, and landing will transfer its weight to the support. Okay, okay. Perpendicular riser, which riser equal to 150 mm and thread equal to 280 mm. So riser is 150 mm and thread is 280 mm. The height of the story is 3 meters. Height of the story is 3 meters. Okay. And the width of the flight is 1.5 and landing is 3.15. This is width of the landing 1.5, width of flight 1.5, width of landing 3.15 meters. Okay. Assume the live load to be 3 kN per meter square. Use M20 grade concrete Fe415 steel, and weather condition are mild. Okay, when the weather condition is mild, we will consider clear cover as 20 mm. So given to us, riser is 150 mm, thread is 250 mm, Fi is 415, FCK is 20, width of flight 1.5, width of landing 3.15. Let us calculate the number of steps required for climbing the story. Okay, number of riser required is equal to height of the story, that is 3 meters 3000, divided by height of riser 150. So this is equal to 20. We have to provide 20 risers. Okay, so this is first riser, this is 10th riser, this is 20th riser. We have provided 20 risers. So the number of tread will be equal to 18. Okay. Now effective span. Okay, we fall in this clause with the spanning on the edge of the landing slab, which spans parallel with the riser. Okay, the spanning of the landing is in this direction, which is parallel to the riser. Okay, so in that case, the effective span has to be taken from center to center of this landing. Right? So this is 1.5, this is 1.5, so this is 0.75, this is x, this is x, this is y, this is y, right? So in this case, this landing spans in this direction when you consider this flight. But when you are doing the design of landing, then it will span in this direction, right? So in this case, that the total load coming on this landing in kilonewton per meter square has to be taken half in this over here, right? When we consider the design of this flight, right? So this is what we'll see further. Okay. So first we will find the effective span of stair. Okay, the effective span of staircase supported on site. This is a table given in the code. Okay, so we have to see that in which criteria do we fall. X is equal to 0.75. Okay, which is less than 1 meter. Y equal to 0.75 meter, which is less than 1 meter. So we follow this criteria. That is G plus X plus Y. Okay, that is equal to, this is X, this is G, this is Y. Okay, so if this X were greater than 1 meter, then we would have to take X equal to 1 meter. X and Y cannot be greater than 1 meter, right? Then if it is found to be greater than 1 meter, then we have to take 1 meter, right? But our X and Y are less than 1 meter, so it is G plus X plus Y. So our effective span is 0.75 plus 2.52 plus 0.75, that is 4.02. Assume the effective depth of the west slab equal to span divided by 28, that is 4.02 divided by 28 is equal to 118. We will assume this is effective depth. Okay, we will assume overall thickness of west slab is 175 perpendicular to the west slab. So this is 175. Okay, now we have to find this d because we are finding the load on the horizontal projection. Okay, so we'll have to take the this d for finding the weight self weight of the west slab, right? So this d, first you have to find b. B is, this is b. B is equal to under root t square plus square, that is equal to 317.65. This d is equal to thickness of wet slab into b divided by t equal to 198.53. So this D is equal to 198.53, right? So this is the formula that is used for finding the waist slab, self weight of waist slab. 25 into this D, and self weight of step is 25 into 0.5 R. Okay, we are taking this triangle as equal to an equivalent rectangle, right? So this is the formula for finding the self weight. So let us find the self weight on load ongoing. Self weight on slab is 25 into D. This D, that is 198, that is equal to 4.955. Self weight of step, that is 0.5 into R, that is 1.875 kilonewton meter square. Uh, Floor finish is 0.75 kilonewton per meter square. Load, live load, we are taking as 3 kilonewton per meter square. So total factor load on going. This is going, okay. This is our going, okay. Total factor load on going is found to be 1.5 into summation of this loads, that is equal to 15.86. Okay, this is 15.86. Okay. Now let us find the total load on landing. Self weight of landing is self weight into self weight of waist slab. In case of landing, landing is horizontal in direction. The D will be equal to 175, right? So that this D will be equal to 175. But I have taken equal to 198. Okay, so it will give a little bit higher load, and the design will be a little bit conservative. Don't worry. Okay. So self-weight of lending, okay, I have written a Westlab, but actually I have taken D for this Westlab, so I have written Westlab. But you can take lending over here, that is 175, D equal to 175. But I have taken 198, okay. So the load is found to be 4955 kilonewton per meter square. Floor finish is found to be 0.75 kilonewton per meter square. Live load is 3 kilonewton per meter square. So total factor load on landing is 1.5 into summation of this load, that is 13.05. Okay. Please remember now, as I told you, that this part of landing, when we are designing the flight, it spans in this direction. But when we will be designing the whole landing, then the landing will span in direction. So the loading to be taken in this area has to be half of this total load which we get for the landing. Okay, so the total load on the landing which we get is 13.05. So we have to take half of that. Okay, so this is equal to 6.52. So this is how we get the loading. Sorry, you can see the loading is symmetrical. So RA will be equal to RB. So RA is found to be 24.88. As the loading is symmetrical, the maximum moment will be found at the midspan. Okay. So at midspan, the bending moment is 29.42. Okay. Now we will have to calculate the steel required for the moment 29.42. Sorry. So let us first find the effective depth D. That is capital D, that is 175 minus clear cover minus the diameter of the bar divided by 2. We are assuming 12 dia bar as our main. So 175 minus clear cover is 20 minus 6, that is 149. Okay, putting the values of M and D over here, we get AST is equal to 596.74 per meter. Okay. Okay. We are designing this staircase for 1 meter width. Okay. Because it is a slab. We are considering this as a slab, so we are designing this as a 1 meter strip. Okay. So this is how we got the EST, that is 596.74 per 1 meter. Now, finding the spacing for 12 mm, considering the 12 mm dia bar as main steel, we get 189.36 mm. Okay, so let us consider provide 12 mm diameter at 175 center to center spacing. Right? So this is what we are providing in the flying portion. Okay, so this is the flat portion. This is the main steel. We are providing 12 mm at 175 mm center to center, right? Okay. Now we will find the distribution steel required, okay, in the flight. So first we will do the check for shear. Corresponding tau C for this PT. Okay, this is provided as we have reduced the spacing. Of course, our PT provided will be increased. Okay, so now it is 645.71. So PT is 0.433. Corresponding tau C we find 0.45. For PT 0.433 FCK20. from IS 456 2000 table 19. So nominal shear stress tau V is equal to reaction divided by VD. So reaction we found as 24.88. So 24.88 divided by 1000 into D is 149. So we get tau V as 0.167, which is less than 0.45. So okay, right? So now let us find the distribution of steel in flight. Okay, so EST minimum is equal to 0.12% of into B into D. Okay, B is 1000, D is the thickness of the slab, that is 175, and that is equal to 210 mm square. So we will provide 8 mm bar as distribution steel at 220 mm, which should be lesser of the this to 5D or 450. D is 149 into 5, that is more than 500, this is 450. So we are providing 220. So that is it. Okay. So let us see in the diagram. All these dots are the distribution still in the flight. Okay. So 8 mm dia about 220 mm center to center. That is what we are providing. Okay. Now coming to the design of landing, right? Design of landing. Uh, so now we are going to design this landing. Okay. So half the weight of this is going to fall on this landing, and half of the weight of this going to fall on this landing. Similarly, half here, right? So uh, we will have to take two loads. One, the total load on this landing, another, the load coming from this going, right? So the entire loading on the staircase is transmitted to the supporting edge by the bending of landing slab in a direction parallel to riser, right? So the slab is going to bend in like this and pass on the load to this support and this support, okay? So that load will be W, and you will get two reactions, RB and RA. So let us find the loads. A direct load on landing considered full width, we had found 13.05. Total load coming on landing. Total load coming on landing was 13.05. Okay. So we have to take that load into width, full width. Okay. The width is 1.5. So into 1.5 will give you 19.575 kilonewton per meter. So we got load in this direction per meter, right? Now, load from going. Okay, the load from going. This is 15.86 kilonewton meter square. This is going. Okay, so half the load. Okay, half the load will go to this landing. Half the load will go to this landing. The length of this going is 2.52. Okay, so total load of going in meter square into 2.52 divided by 2. Half the loading will come to this landing. Okay. So this is equal to 19.98. Right. So the total load on the landing is this plus this. Okay. Now we want to find, we are designing a 1 meter strip. Okay. So total load divided by 1.5 will give us a load for 1 meter strip. Okay. Taking 1 meter strip for landing load, for 1 meter strip, W is equal to this plus this divided by width. That is equal to 26.37. Okay. So now this is our W. Okay. Effective width of landing, that is this, is 3.15. Okay. Reaction is W into L divided by 2. RA is equal to 41.53. RB is equal to 41.53. W, we can find a moment, maximum moment at the midspan, that is W square by 8, that is 32.7 kilonewton meter. The effective depth D is found to be 149. So putting the value of MU and D in this formula, we get EST as 670.8 mm square per meter. Okay. Now we are designing landing. Okay, we have already designed the flight. Now we are doing the design of landing. So let us find center to center spacing. We are going to use 12 mm steel, so that is equal to 168.45. So let us provide 12 mm bar about 150 mm center to center spacing. Right? So EST provide is definitely going to increase. So it will be 753.33. PTV is found to be 0.505. Okay. So this is what we are providing in our landing. So this is the main steel of landing. Okay, right? So that is 12 mm at about 150 mm, right? And this round dots are the steel coming from the flight, right? We have provided 12 at 175 center to center, right? And at top we can reduce the main steel of this flight. And then you can provide 12 at 300 center to center, right? Okay. Now check for shear for landing. Corresponding tau c is found to be 0.48 when PT is 0.505 and FCK is 20 from table number 90, IS 456 2000. Nominal shear stress V divided by VD. Okay, V is your RA, which we found, RA 32.7. Okay. Oh, okay. RA is to be taken as 32.7, right? It is by mistake taken as 41.5. Please, okay. So it will be still lesser than this, which is already less than 0.48. Okay. So it's safe. Okay. So we will provide 12 diameter at 150 center to center as the main inlet, which we have provided, right? So this is the complete design. Uh, this round bars at top and bottom are of landing that is provided at 12 150 Okay, this dots are the distribution steel for the flight, that is 8 and 220 and this is the main steel for flight, that is 12 at 125. Okay, so this is how we can draw, we can do the reinforcement detailing of this staircase, right? Okay, now taking the same example, but we will take as thread riser type staircase. Okay, so given to is riser 150 thread 280 F5 415 FCK 20 width of flight 1.5 width of landing 3.15. Okay, and we know we have to give 20 risers. Okay, as seen in last example. And our effective span was found to be 4.02. So let us assume the effective depth of the base slab equal to span by 28, that is equal to 113. Let us assume the overall thickness of third riser slab equal to 150 mm. Okay. So thickness we are going to assume as uh, thickness is, we are assuming as 150 mm. Thickness 150 mm. Okay. Right. Now self-weight on going. Okay, self-weight on going. So this is the formula which we have already studied for finding the self-weight of third riser slab, which is 5.758. Finished floor load is 0.75 kilonewton per meter square. Live load is 3 kilonewton per meter square. Total factor load is 1.5 into summation of these three loads, that is 14.262. So 14.262 is the load on going. Okay. So again, now finding the total load on landing, self weight of west slab is 3.75 kilonewton per meter square. Floor finish 0.75 kilonewton per meter square. Live load 3 kilonewton per meter square. Total factor load 1.5 into summation of these three loads, that's 11.25. Okay, but again, we will consider only half over here, as we know that this landing is spanning in this direction when we are considering this flight. But when we will be doing the design of landing, then this will span in this direction. So over here, we'll take only half of this load, okay? Because the load is coming from two systems, right? Okay. So calculation of bending moment maximum at the midspan and the calculation of the shear force that we that R and RB. As the loads are symmetrical, RA will be equal to RB. RA is equal to 22.188. MU at the midspan is found to be 26.38. Okay. So find the effective depth D, that is equal to 125. Total depth 150. Clear cover 20. We are using 10 diabar. So 10 divided by 25, that is equal to 125. So putting this value, we get A is equal to 656.31. Center to center spacing turns out to be, we are taking 10 steel over here. Okay. Okay. Now this is end thread riser slab. Okay. So the stirrups will be these are the stirrups. Okay. This this stirrups will be the main stirrup. Okay. So these stirrups are we are taking of 10 diameter, right? Okay. So the spacing required comes out to be 119. Let's provide 10 dia stirrups at 110 mm center to center spacing. As we are reducing the spacing, EST provided will be increased. PT will turn out to be 0.5709. Check for shear. Corresponding tau C is found to be zero point 0.5, but PT when PT is 0.5709, FCK is 20. Okay. Nominal shear stress is simple RA you got as 22.188 divided by 1000 into D is 125. You get 0.177, which is less than zero point 0.5. Okay, right? Now our main steel was found to be 10 dia about 110. Okay, so our main steel, right? This is our main steel. So stirrups I have shown over here two length 10 dia about 110 center to center main reinforcement. Distribution will be just 8 bar at each corners in case of flight. Okay. Now coming to the design of landing. The entire loading on the staircase is transferred to the supporting edge by bending of landing slab in direction parallel to the stairs. So half the load of going is transferred over here, other half is transferred over here, and this landing will span in this direction and distribute the load to the side support. Okay. So again saying direct load on landing considered for full width. This is 1.5 width. That load coming on the landing which we found over here, okay, was total total factor load on landing was 11.25. So over here we take the same 11.25 into total width 1.5, that is 16.875. So we get load in kilonewton per meter in this direction, right? Now load from going, okay. So load from going is 14.262, okay. So half the load over here. So 14.262 into this height, this length is 2.52 divided by 2, right? So this is how we get the load from going as 17.97 kilonewton per meter. Okay, like this. So total is equal to this plus this. Now taking 1 meter strip of landing. Now we will design this strip as 1 meter design strip, right? Taking 1 meter strip of landing load per 1 meter width W is equal to this plus this divided by width of this. Okay, that is 23.23 kilometer meter. So this is the W which we get. So reaction is simple, WL by 2, that is 36.58. This is the effective span 3.15. Okay, maximum moment at center WL square by 8, that is 28.8. Effective depth D is found to be 125. We are assuming 12 dia bar. Okay, in landing also as mainstay. Okay, so ESC we are finding at 726.3 meter. Center to center spacing is 108. So we will provide 10 dia bar at 100 center to center spacing in landing. Okay, so this is our main steel for landing. We will provide 10 about 100 center to center. This round bars section are the steel coming from the line. Okay, right. So once we have once we have found the steel required, spacing required in landing, okay, then we can find AST provided. This is 785. PT provided is 0.628, and we will do the check for shear for landing. Tau C is found to be 5.525 Newton per mm square for PT 0.628 and FCK 20 from table 19 of IS 456 2000. Nominal shear stress is reaction divided by BD. Reaction is found to be uh, reaction 36.58, right? So 36.58, so divided by BD is 0.292 Newton per mm square, which is less than tau C. So okay. So provide 10 dia bars at 100 center to center spacing main steel, which we saw here, and below detail below shows the detailing of the steel in landing portion. Okay, so this is the section, and this is a longitudinal. This is longitudinal section, and this is the transverse cross section of the landing. So this round bars are the main steel of landing, and this straight bars are the main steel coming from the line. Okay, so that are, and this coming from flight is 10 mm dia, about 110 mm center to center, and spacing that for landing is 10 mm, about 100 mm center to center. Okay, so this is how you can draw a complete detailed section as a just the design. The top round bars are the main steel of landing, which are 10 mm or at about 100 mm center to center landing reinforcement over here also. And steelers in this case, okay, are the main steel for flight. Okay, so that is two leg 10 mm dia, about 110 mm center to center main reinforcement. This is for flight. Okay, so this is how you can do the detailing. Right? Now coming to the next problem: design and detail an open well vest slab type staircase as shown in figure. Okay, it is supported over here, 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 it is supported over here. So this flight will span like this flight will span like this flight will span like this. Now this landing area is common to this flight and this flight. This landing area is common to this flight and this flight. So whatever load on this landing we get, we have to consider half in this direction and half in this direction. Okay. So we will design this flight. Okay. Now given to us. Okay. Taking landing and flight width equal to 1.5 meter, 1.5 meter, 1.5 meter. Okay. Take riser equal to 150, tread equal to 280 mm. Use M20 concrete, Fe415 steel. Assume live load is equal to 5 kilonewton per meter square, and assume mild exposure condition. So clear cover we will take as 20 mm. Riser is 150 mm, tread is 280 mm, Fi is 415, FCK is 20, width of flight is 1.5, width of landing is 1.5. Now, first we will find the loads ongoing. Okay, loads ongoing. The total effective span is 4.68, right? Let us assume the effective depth of best slab equals span divided by 88. That is 4.68 divided by 28. 1 is equal to 0.167. Let us assume overall thickness of best slab equal to 200 mm. So that is equal to 200 mm. Okay, now we have to find the load on the horizontal projection. So we have to find this D, right? So for finding this D, we have to find first B. B is this, that is equal to under root of T square plus R square. Okay, so that is 317.65. So again using the same formula, self weight of west slab is 25 into D. This is D, this D, this D is this D. Self weight of slab is 25 kN per meter cube into 0.5 R. So D is equal to thickness of west slab 200 into B by D, that is 226.89. This is 200 and this D is 226.89. So self weight of slab is 5.672. Self weight of step is 1.875. Finished load is 0.25. Live load is 5 kilonewton per meter square. Okay. So effective load is 1.5 into summation of this load, that is 19.94 on going. Okay. Now finding the load on landing. Self weight is 5.672. Finished load 0.75. Live load 5. Total factor load 1.5 into summation of this load, that is 17.13. We have to take half of this over here, right? As we have understood, as I've explained, because the load are common for the two systems. So this is our flight section. The loading is symmetrical, and so RA will be R equal to RB. RA is found to be 29.6, and the maximum bending moment at the mid span is found to be 41.805. So calculate effective depth D. Okay, capital D, that's 200 minus clear cover 20. We are using 12 mm diabar, so 6. So effective depth D is 174. We get ESP as 7 to 9.18 mm square per 1 meter because we are designing 1 meter strip. Okay. So then center to center spacing is 154.96. Let us provide 12 mm at about 150 mm center to center spacing. Okay. So this is our main steel which will provide 12 mm about 150 mm center to center, right? Okay. Now check for shear. Uh, Corresponding tau CV is found to be 0.45. This is our ASC provided. This is our PT. And so tau C is found to be 0.45 for this PT when FCK is equal to 20 using table number 19 of IS 456 2000. Okay. Nominal shear stress V by BD. This is reaction. Okay, which we found for reaction is 29.6. Okay, 29.6. So we get tau V is 0.170, which is less than tau C, so same. Okay, so distribution still required in flight. Okay, these round dots are the distribution still. Okay, required in flight. That is 0.12% B into D, 240 mm square, provide 8 mm about 200. Be less than 5D or 450 mm, lesser of this two. Okay, okay, so it is okay. So provide 8 mm dia about 200 mm center to center. This is distribution still, right? Now this steel is continued over here. This steel is continued over here. Okay, so this is also 12 mm dia at 150 mm, and this is also uh, 12 mm dia about 150 mm. Okay, now this round bars, okay, shown at top and bottom are the landing steel. Okay, that is main steel of landing. 12 mm dia about 150 mm center to center, right? Okay, also. So this is how you can do the detailing of the base slab. Okay, so we have designed this slide, right? Okay, similarly, you can design this slide and this slide also, right? So we can see over here, okay, uh, that the support is at the side edges of the landing as shown over here, right? So hope you must have found this video useful. Uh, Thank you.